So what did I miss? What did I miss?
Welcome to this edition of So What Did You Miss from Monday, October 19th and Tuesday, October 20th. In class today, we practiced applying Newton's three laws of motion and defined Newton's third law as well. We also differentiated between mass and weight, which is another name for the force due to gravity, all through some Nearpod slides that can be found in my MCPS classroom under the Week 8 module. So if you were absent from class, I do expect you to go through and complete those. So to show you where that is real quick, if you click on the modules page and look under Week 8, you will see this page here that says Week 8 Notes and Learning Resources. That is where you will click to have access to the Nearpod slides from class today. All right, so let's go ahead and dive on in here. So we did some open-ended questions and some multiple choice questions today. Now, one of the ones we looked at is how to look at a situation where you have a 10 kilogram object traveling with a velocity that's shown on a velocity time graph. And our goal was to ultimately find the net force. And so if you look closer at our velocity time graph, this is where things connect together from what we were learning previously to what we're learning now. And if you look at the velocity time graph, remember that a change in velocity over time, our rise over our run, is going to give us acceleration. Remember, acceleration is defined as the change in velocity over a period of time. So if I take the slope of my graph, which in this case, if I picked my first and last points, I would rise 50 and run 5. That would give me a slope of 10 meters per second, or meters per second squared. And I could pick any 2 points on this line and I would get the same slope value. So the first step was to use what we knew about velocity time graphs to discover our acceleration. We can then use that paired with the mass given in the problem of 10 kilograms in order to find our net force using Newton's second law. Remember, Newton's second law states that the net force is equal to our mass times our acceleration. So you would go ahead and be able to write your answer in here and solve. So I'm not going to give it away, but you should be using your acceleration, your slope, and the mass here so that you can solve it. So again, slope is acceleration on a velocity versus time graph is the first concept. And the second concept you'd use for this problem is the net force is equal to your mass times your acceleration. And you should get a nice whole number answer for this question. All right, our next question dealt with the relationship between net force and acceleration using Newton's second law. So Newton's second law, remember, is the net force is equal to mass times acceleration. All right, and if we look here, we have the acceleration of an object with a mass of 1 kilogram is 5 meters per second squared. If the net force is tripled, then what would the new acceleration become? And so we know from the beginning part that the net force is equal to 1, which is the mass, times the acceleration, which is 5, which gives me a net force of 5 newtons. This means that my new force, pick a different color here, would have to be 3 times that size. It would have to be 15 newtons. And it would still equal 1 kilogram times my new acceleration. Now, you could solve this by dividing both sides by the mass and getting that the acceleration also becomes 15 meters per second squared in this case. Or you can use the relationship that exists between mass and force. Mass and force are directly related to one another meaning that if you increase the net force by a certain amount, then that means the acceleration also increases by the same amount. So if you triple the force, then you're tripling the acceleration as well. If you were to divide or reduce the force, let's say we made the force 3 times smaller, then you would do 5 divided by 3. It would be 3 times smaller than it is right now. So that is how force and acceleration are related. It is a directly proportional relationship. So whatever happens to one happens to the other. And so that exists between force and acceleration. The next thing we did was some drag and drop notes where we filled in the blanks together. So let's do that now. So mass and weight are not the same thing. Weight is also known as the force due to gravity. So we're going to drag and drop gravity. And it is how your mass is affected by that force due to gravity. Now, mass never changes when an object moves to a different planet or location in space. And a good way to think about it is mass is how much stuff you're made of. And so if you were to go to like the moon or to Mars, it's not like you would go and leave part of your body behind, like you would take your whole self with you. So your mass is going to stay the same. The amount of stuff that you're made of is going to stay the same as you travel through the universe. Now, the weight or force due to gravity will change because that is dependent upon the acceleration due to gravity on that planet, moon, star, etc. So these are the blanks you should have filled in for our first set of notes. That weight, aka the force due to gravity, is how mass is affected by gravity. And it is not the same thing as mass. Mass never changes when it moves to a new planet or in the universe. And mass is also measured in kilograms. That's your big clue that it's a mass and not a weight or a force, is if it is measured in kilograms. While weight is a force and should be measured in newtons. So remember to hit done, move on. So we can use Newton's second law, F equals ma, to find the force of gravity on a specific planet or star or moon by taking the mass of the person or object and multiplying it by the acceleration due to gravity on that specific location. So on Earth, the acceleration due to gravity is always going to be what we round to -10 meters per second squared. So we can find the weight of any object near the surface of the Earth by taking its mass and multiplying it by the acceleration due to gravity. And we went ahead and we tested that out in class today. So we took the weight of an 85 kilogram person on Earth and compared it to the weight of that person on Mars, where the acceleration due to gravity is much less. It is 3.2 meters per second squared, while on Earth it is 10 meters per second squared. And so I gave you guys the equations. All I wanted you to do was the multiplication to see which force was larger. And using the Drawlet tools, you'd show your work in the Nearpod. So again, I gave you guys the mass of the person, which will stay the same on Earth and Mars. And I gave you the accelerations. And so you would go ahead and show me your work for the force on Earth and then for the force of gravity on Mars and see how they compare. Just to check your work, the weight of the 85 kilogram person on Earth should be 850 newtons, so 850 newtons. And the force of gravity or weight of that same person on Mars would be 272 newtons. Now that makes sense because if we look at our question, our acceleration due to gravity is 3.2 meters per second squared on Mars. On Earth, it's 10 meters per second squared. And if you were to multiply 3 times 3, you'd get pretty close to 10, especially 3.2 times 3. And so it makes sense that the weight on Mars would be about a third of what it is on Earth because the acceleration is less. And remember, force and acceleration are directly related to each other. So to summarize, the mass of the person is 85 kilograms no matter where they go in the universe, while the weight does change, and it so happens in this example, the force of gravity on Earth should be larger than the force of gravity on Mars. Now, this brings us to our discussion of Newton's third law of motion. Now, the official definition of Newton's third law states that whenever a first object exerts or makes a force on a second object, that second object exerts a force equal in magnitude and opposite in direction on the first object. So that's pretty fancy. What it boils down to is that every action has an equal in magnitude, in amount, and opposite in direction reaction. To give you an example, if this is a person, the force of the person on the wall equals the force of the wall on the person. The two objects interacting would be the person and the wall. And you can see from the arrows that those forces are equal in magnitude and opposite in direction. So for our fill-in-the-blank notes for Newton's third law, the third law focuses on action-reaction pairs of forces. They always exist in pairs for the third law. That happen when two objects interact. So for Newton's third law, two objects need to be involved. This is different from our other two laws of motion, where we're looking at just a single object at a time. These forces never cancel out because they are on different objects. So if we were drawing free body diagrams, you would need two diagrams because there are two objects, and there would only be one force on each diagram, so that's why they're not going to cancel with each other. Scrolling down. To describe a third law pair, all you do is switch the wording around. So the force of the person on the wall is equal in magnitude and opposite in direction from the force of the wall on the person. So that wording is something we're going to use. So the force of the person on the wall is equal and opposite to the force of the wall on the person. So we're switching those words. Some more third law pair examples would be the force of a hammer on a nail is equal in magnitude and opposite direction of the nail on the hammer. We also have the force of the earth pulling on you is equal in magnitude and opposite in direction of the force of you on the earth. Now I know that seems hard to believe, but for Newton's third law, the two things interacting will always experience the same amount of force in opposite directions, but that doesn't guarantee that they're going to react the same way. Now, before we get to how things will react, make sure you share using the proper wording. So again, the examples I used was the force of a person on the wall equals the force of the wall on the person. So I want it in that format where the words switch. So when you type in your example here and post it, make sure to use that format. Like the force of the first thing on the second thing equals the force of the second thing on the first thing. Final concept from today is just because two objects experience the same amount of force does not mean that they will accelerate the same. And for our example, we talked about the force on a truck and a train in a collision. You can see that the forces are equal in magnitude and opposite in direction from the graphs. The truck's force is above the x-axis, while the train's is below. But because of Newton's third law, we know that the forces on each are equal to each other. So the force of the truck must equal the force on the train. Now, if we take that one step further, that means the mass of the truck times the acceleration of the truck equals the force on the truck because of Newton's second law. And same thing with the train. The mass of the train must equal, or times the acceleration of the train must equal the force on the train. Now, in order to keep things balanced, keep things in check, that means that the smaller object would have a larger acceleration, and the larger object would have a smaller acceleration. So I'm going to demonstrate this with numbers because sometimes it's easier to see with numbers. So I am going to pick a random amount of force that the truck and the train are going to experience when they collide with one another. So I'm going to go ahead and choose that value now, and I'm going to make it pretty big. I'm going to say that they experience a 5,000 Newton force. Okay, so I know my force is 5,000 newtons, and I'm going to shift that so that it's a little easier to read. So 5,000 newtons is acting on the truck, and 5,000 newtons is also acting on the train, because the size of those forces must be equal according to Newton's third law of motion. All right, so I'm going to go ahead and set the mass of the truck to be 500 kilograms. And that times my acceleration. In order to get 5,000 newtons, I would need my acceleration to be 10 meters per second. But the force on the train also has to be 5,000 newtons, and the train has more mass than the truck. Trains are bigger. So let's say that the mass of the train happens to be 5,000 kilograms, that it's much bigger than the truck. That would mean in order to get a net force of 5,000 newtons, my acceleration would need to be a lot smaller. It would need to be 1 meter per second squared. So if we look at that, it's like a little balancing act almost. The smaller massed truck has a larger acceleration of 10, where the larger train has a smaller acceleration of 1 meter per second squared, in order for both forces to be the same size. And so this not only applies to collisions with like large and small objects, but this also could apply to that earlier slide that I mentioned where I said that we pull on the earth the same amount that the earth pulls on us. But when we compare our mass to the mass of the earth, our mass is tiny. It's almost non-existent. The earth has a mass of 6 times 10 to the 24th kilograms. That is the number 6 followed by 24 zeros. So that's pretty large. And our masses, in high school, I would say like for an adult, you would be anywhere from like 45 kilograms to like 200 kilograms, which is way smaller than 6 times 10 to the 24th kilograms. So when we think about the fact that we pull on the earth the same amount that the earth pulls on us, well, really, in reality, like, yes, we pull on each other the same amount, but our acceleration of 9.8 meters per second squared is the large acceleration, and the acceleration on the earth, the much larger mass, would be much, 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 much smaller. Now, this also lines up with Newton's first law, the law of inertia, with what we'd expect to happen. We know that inertia is defined by the amount of mass something has, and so the more massive an object is, the more mass it has, the harder it is to change how it's moving, the harder it is to get it to accelerate. So it would make sense as well that the smaller mass would accelerate more, and the larger mass would accelerate less because of that idea of inertia. The more inertia something has, the harder it is to change its motion. And so this kind of connects together all of our laws of motion. And another example that pulls together the forces between objects, Newton's third law, and includes the Earth would be like the Earth and the Moon. So the Earth is still bigger than the Moon, but the Moon is a lot closer in size to the Earth. So when the Earth and the Moon pull each other in a third law pair, because the force of the Earth on the Moon is equal in magnitude and opposite in direction to the force of the Moon on the Earth, we know that that exists because we know the Earth pulls on the Moon because the Moon goes around the Earth. So that's caused by that pull of gravity in from the Earth. That's why the Moon orbits our planet. Now, the Moon does pull back, and we actually can see it pulling back, and we can see that with ocean tides, with how high the water in the ocean is. And so that is a great example of how there is a pull, it does exist, and while both the Moon and the Earth are experiencing the exact same amount of pull, they are not accelerating, they're not changing their velocity in the same way because they are different sizes. The bigger mass will always accelerate less. The smaller mass will always accelerate more. The big key takeaway, though, is that the forces acting on both objects in a third law pair must be the same size. All right, well, the last thing we went through in class was quiz format. So as a reminder, our next live class, there will be a quiz on Newton's 3 laws of motion. And we'll look at some study resources that are available to you before we end here. So let's go ahead and do that real quick. So if you go to our course modules page, you can see quiz review and then how should I study. So let's go ahead and start with quiz review. Now I did post the quiz review here as a PDF. The first part is going to involve some vocabulary and concepts. It's almost like fill in the blank. The next section is going to deal with multiple choice questions. Finally, followed by some third law pair, practicing identifying third law pairs. And then some practice problems with calculations. Now, in order to get you guys feedback, I've got this here, and you can print this if you prefer to have like a hard copy. There is a link in case your Google Drive authorization isn't working still, so that you could print or open this document. But what I'm going to create is a practice quiz, an ungraded quiz, essentially, where you could type in your answers to this worksheet and then get feedback to know which ones you got right and which ones you still need to study. I don't want to post an answer key because I know if I just post the answer key, some of you will be tempted to just look at that without trying the problems first. So definitely use this to study. The other resource you want to use is the next page in our classroom that deals with study resources. It goes through why you should study. I've got the up-to-date forces fact sheet that includes all 3 laws, drawing force diagrams, and just like the last quiz, you will have access to it. I've also included the motion fact sheet in case you wanted to review any vocabulary like velocity, acceleration, what the slopes on graphs mean. That is there as well. Again, the quiz version will be posted here once it is complete. And then finally, there are some concept builder questions that I think could be useful. The unbalanced balance forces practice is really great because it will help you identify if an object is going to speed up, slow down, or move at a constant speed based on a force diagram, and also to identify if the forces are balanced or unbalanced. Remember, if they're balanced, it's in equilibrium, following Newton's first law. If they're unbalanced, it will accelerate and follow Newton's second law. So being able to identify that is crucial and something that could be good practice for the quiz, and you'd get immediate feedback. The next practice that's linked here is match that free body diagram. So it's essentially multiple choice. There's a couple levels that you can play at, and basically a scenario is described, and you're going to pick from the options which force diagram best describes what's going on, and you'll get immediate feedback again if you've matched them correctly. Finally, you have the second law simulation here, where it's very similar to what happened in the Nearpod earlier, where I asked what happens to the acceleration when you triple the force. It's looking at the relationship between force, mass, and acceleration, and how changing one of those items affects the others. So you can pick and choose which review materials work best for you. Again, if you still owe me the forces FET activity, the due date for that is Monday, October 19th, with a deadline of Wednesday, because I do highly recommend that you practice using it before the quiz, because it will give you practice with F equals MA, with analyzing graphs, all skills that could be useful on our quiz on Thursday or Friday. If you have questions before the quiz, I was live on October 19th from 2:45 to 3:15, and I am available for Wednesday check-ins during periods 1, 2, 4, 5, and 7. So if you have any last-minute questions before you take the quiz, that would be what you need to do. So have a great rest of your day, and if you owe me work, Try to get it done. The asynchronous work this week is to study. So there's not going to be anything you submit, but you should absolutely practice and study for the quiz so that you are most prepared, and or catch up on some work that you owe me. So use this time wisely. And if you need anything, I will see you on Wednesday.